Hi everyone, welcome to the technical briefings on software engineering for data analytics. This is our last technical briefing session, and before we actually start this session, actually we'll have just 1 or 2 minutes to let other attendees to join, because sometimes they are kind of looking around the other session. We'll try to find them connect, so we'll just wait just 1 more minute. All right, welcome again. So welcome to the technical briefings on the software engineering for the data analytics. I am Eunji Song from Baylor University. I'm the one of the co-chair for these technical briefings. And today we are going to talk about the software engineering for data analytics with Dr. Marian Kim. But before actually I formally introduce our speaker, just give us some preliminary information for your attending. So this will be held as a Zoom webinar. So this webinar form will give us to talk or interact through the Q&A box. So as an attendee, you can post your questions to Q&A. You can find the Q&A interface from the bottom of your Zoom menu. So if you open the Q&A box, you can post your questions. Feel free to ask your question during the talk for some clarification, and I will moderate as needed. And also we'll have some QA session after the talk. And through this QA box, you can actually vote for questions you like to see what is the popular ones in our question list. And also you can add your comment for other questions. So we want to use this medium as a kind of way to have our discussion as interactive as possible. All right, so we have an interest talk by Dr. Marian Kim. She's currently at the University of California in Los Angeles. She's currently actually joining from Germany. And she has a long list of awards and fellowship that include the NSF Korea Award, and also she has a lot of fellowship from including the Google, and she has been a leading person to work on the defining engineering area of the software engineering for data science, and then she's currently lead the group for software engineering for AI and machine learning based systems. So I'll just give the mic to the Marian. All right.
Thank you, Eunji, for introduction. It's really my honor to give a technical briefing talk on this topic of software engineering for data analytics and AI and machine learning, which I call as a software engineering for data analytics. We are at an inflection point where software engineering meets a data-centric world. And using this technical briefing talk, I would like to make a very strong case that we should rethink existing software engineering techniques such as the debugging and testing and design to meet the demands of AI, machine learning, and big data analytics. What is a confluence? This term means where two rivers or flows meet. I learned this lens from my colleague, George Verghese at UCLA. There has been many interdisciplinary thinking born out of where two streams of ideas meet and create a new stream of transformed ideas starting from that inflection point. Good example is an impressionism where a realistic painting and psychology meet and subjective perceptions are expressed in terms of a brush stroke and light reflection. I feel that personally right now is this inflection point where existing software engineering, the kind of work that we do as a software engineering researchers to improve correctness of software and to improve developer productivity meet data-centric disciplines such as machine learning, AI, and big data. Before I go into the main part of the talk, this is a takeaway message that I want to convey. Ensuring correctness is a huge problem in data analytics. And at this inflection point, somehow many of the software engineering researchers have gravitated to applying like AI, machine learning, and big data to existing software engineering problems, as opposed to redesigning and adapting existing software engineering to meet these new requirements of data analytics. And in my opinion, software engineering for data analytics is not a straightforward extension of existing software engineering research. There are many exciting open problems in this domain, and we should be working on these kinds of problems, which I want to sketch as a part of my talk. Almost on a daily basis, you will hear about self-driving cars, drones, and companies are hiring data scientists and AI workforces. And there are even fear that this AI will mess with our current world, right? And then create the bias. And data analytics are in high demand indeed. If you look at this chart, the growth of a data analytics based hiring or hiring in data scientists has increased dramatically over the years. But we also hear problems of misleading or wrong diagnosis, inaccurate predictions and interpretation of a result. News also tell us how these data analytics and AI could result in deadly consequences in our daily lives. In the case of Uber, the consequence was fatal. In March 2018, self-driving Uber vehicle killed a woman with a bike and shopping bag. This rise of a data-centric discipline, such as AI, machine learning, and big data, has impacted our own software engineering research community as well. In preparation for like ICSE keynote, Automated Software Engineering Conference keynote last year, I did a manual analysis of about 300 papers over 10 pages in the last 4 years of ICSE proceedings, categorizing the research problems that it's addressing and the approach being used. As you can see as an orange color in the chart here, number of papers that employ data science and AI and machine learning and big data has grown substantially over the years. But most of these papers are applying data analytics to existing software engineering problems, such as a defect prediction, bug finding, program repair, document generation, summarization, and code recommendation and testing. This is also aligned with the rise of sub-research communities, such as a mining software repository and search-based software engineering. It's perhaps because using techniques such as deep learning, natural language processing, heuristics or multi-objective search or classifications or information retrieval could give some extra boost for hard software engineering problems. However, very few papers, in fact, only 13 in my analysis, are targeting to improve software engineering techniques to enhance the data analytics. It's almost 9 times less than the other paper that uses data analytics to improve software engineering problem. In my opinion, even though this red chart that I have shown here, that's like small piece of pie, I see tremendous opportunity for us to work on. So the rest of my talk is to make a strong case for software engineering for data analytics. In the past 5 years, I have collaborated with Microsoft Research to study professional data scientists. And this study has taught me that this shift to data-centric software development is very real and important. There are key differences between traditional software development and data-centric software development, which actually makes it very difficult to debug and test and ensure correctness. We can easily carve out technical problems in software engineering for data analytics that we could work on. I will share some of my group's research at UCLA and share experience of redesigning debugging and testing techniques for big data analytics application. And then I will conclude with sketching some of the open problems and research directions for us to work together to push this field further. Okay, so let me first share some of our findings from studying professional data scientists in software industry. This work was done in collaboration with colleagues at Microsoft Research. We are at a tipping point where software companies are generating large-scale telemetry, machine quality, and user data. It wouldn't be a lie to say that this rise of big data is really fueled by software industry, where now they are able to log and instrument existing software and services to really capture many kinds of data, on quality, usage, and telemetry. And similar to how we think of software development engineers and software test engineers are established roles in development, data scientists are becoming a part of a software development team. In order to understand what data scientists are, what they do, what kind of challenges that they face, we conducted the first in-depth study of a professional data scientist using interviews. And then we also conducted one of the largest scale survey of a professional data scientist. In our first study of in-depth interviews, we studied and had a 1-hour interview with the 16 data scientists from 8 different organizations, across different product groups at Microsoft. This interview lasted for about an hour. And, we identify emerging themes from the transcribed audio, cluster these themes using qualitative study methods, such as a Venn diagram and card sorting. Then in our follow-up study, to quantify and generalize our findings on skills, working styles, and tools and usages, we conducted a survey with almost 800 professional data scientists. This survey was really comprehensive. We analyzed both, simple answers and long answers carefully. Some of those findings are available as actually both paper and journal paper. But I'm going to maybe sketch some of the highlights that might be interesting for this audience. So these professional data scientists are not have a core training in computer science, and many of them are familiar with the kind of core skill set of machine learning, but come from very interdisciplinary background, ranging from data-centric disciplines such as empirical or experimental physics, finance, bioinformatics, economics, and finance. Also, they have a strong, representation of a higher education degree, 22% about having a PhD degree and about 40% having a master's degree. As I said, we have 2 full papers on this study, but let me share some key findings in the next several slides. This particular chart shows where participants spend their time in terms of activities. These activities are actually from our interview study, which kind of identifies the tasks that they work on. We noticed that people have a different role, which actually really manifested differently in terms of a time spent on these activities. So what I'm trying to show is that, there are many activities that the data scientists work on, but when we actually looked at these time spent, there are like different clusters or sub-roles where people spend different amount of time on different activities. Somebody or you in the audience may think, what does a data scientist mean? Like, is it just a buzzword? To deeply characterize this workforce in terms of skill set, work activities, and background, what we did is actually using this relative time spent data, we use a k-means clustering algorithm and cluster these participants. Then we conducted this statistical test to identify some of the distinctive characteristics of each subcluster that's different from the rest of the population. In other words, what we are trying to do is to really reveal and discover what really data scientists mean by looking at these subgroups and distinctive sub-characteristics of a subgroup to really uncover what data scientists mean. So this analysis actually identified 9 different subclusters or category of a data scientist. And those are described in our journal paper. But let me share maybe 3 example categories to see how these clusters really distinctive from each other. So the first category, I named this category as a data shaper. These category of people are so-called people that you think of as machine learning hackers. They spend significant amount of time analyzing data and preparing data. They have a higher concentration of a postgraduate degree. Many comes with a master's and PhD degree. And they're very skilled with algorithms, machine learning, and numerical optimization. But they are strong in sort of extracting features from data or analyzing data, but often they're not the ones who collect the data. So they're not very familiar with the front-end programming or that is required to instrument the data or to collect the data. We named this category as data shapers because they work on or spend most of time extracting and modeling relevant features from the data. This is the second category of data scientists. We named them as a platform builders because they spend most of their time building platforms to instrument code to collect data. Almost 50% of the time is spent on building infrastructure for data collection and pipelining data from one platform to another. As you can imagine, they have a strong background in big data and distributed systems, and they are also strong in back-end and front-end programming for digesting or processing the data, but also collecting data. Many of them use SQL, and they're very proficient with the mainstream programming languages such as C++, C or C#. We named this category as a platform builder because they really identify themselves as software engineers who contribute to the development of a data engineering platform and pipeline. And they frequently mention the challenges of data cleaning. The next category of data scientists, we name them as data analyzers. They are kind of the people that you think of as a kind of coming with a strong statistics background, or your neighbors and statistics department. Many of them actually hold the official job title as a data scientist. They are strong in statistics like math, Bayesian Monte Carlo statistics, and data manipulation. Many of them are also some of the statistics package users, such as RStudio R users. Many of their programmings are done in this kind of RStudio or stat package or MATLAB kind of format. And they do mention transforming data as a really challenges. And I didn't talk about all 9 categories of data scientists, mention some of these 3 categories as an example. But what I noticed is that among all categories of data scientists, Many of them actually said validation is a major challenge, and there's currently no good method for ensuring correctness of their analytics, data analytics, or predictive analytics application. As a software engineering researcher who work on like techniques like a debugging, testing, or software design and evolution, this was extremely interesting and surprising to me. You know, some of the participants said, honestly, we don't have a good method for this. Just because the math is right doesn't mean that answer is right. And also because many of these data scientists, their outcome is like insights and analytics data, you know, to make it possible for their work to really have an impact within an organization, explainability is extremely important. Like to gain insight, you must go one level deeper. But this was really, you know, in some sense impeded by their lack of confidence on the quality of input or quality of analytics outcome that they generated. So I'm going to stop here a little bit and maybe like invite some questions from the audience. I actually see one question from Jeonjae Kang, right? What is the most practical or popular software for data analytics among data scientists in the industry? So that's a great question. What I wanted to say is that it's very hard to say what is the most practical software or toolkit that they may use for data analytics today. Because as I said, different subcategory of people use sort of different languages and tools and come from different backgrounds. So maybe, you know, that's a sort of my high level answer. But if you go down to deeper, I do have a like concrete data in our journal paper, because what we actually have found out is that this is a subcategory of data scientists differs in terms of their skill set and also tool usages. As I said, you know, for example, the second category of platform builders are familiar with the things like Hadoop, Scope, or Apache Spark, which is very common for building data engineering pipeline. But on the other hand, like the third category of data scientists are heavily geared to, you know, tools like RStudio or MATLAB, because many of them come from sort of a statistics background, right? On the other hand, like, you know, maybe the first category of a data scientist, you know, machine learning hackers are extremely familiar with, or like TLC, which was like a machine learning library in Microsoft, or like something similar to it is like a TensorFlow or PyTorch that is required for building a model, right? So my answer is maybe perhaps a little bit long answer for short question. It depends. And I think that really justifies that we cannot just say that data scientists is one single population, but we need to really look deeper into individual subcategories and how they differ. Other questions from the audience?
I see another question in the chatting window. Question from Srida. There is usually lots of noise in the data. Do you see the need to come up with the precursor approaches for data before going to the next step of the software engineering?
Yes, actually, in fact, many of so in my study, as well as other studies that identified like how AI impacts software development, which I'm going to mention as a part of my talk, these studies actually found that there's like a processes that is required, that's a little bit different from traditional software development. And one of the phases is often like data cleansing or data pre-processing. So to answer your question, yes, like often data cleaning is a big part of the development process and it is necessary. But even having done that, this issue of ensuring correctness is not a solved problem, in my opinion, because you know, the data processing or cleansing code itself could be buggy, right? And also the process or the pipeline is complex, which makes it very difficult to discover traceability across data or increase the visibility and debuggability into data. Yeah.
I think that's all for now.
All right. Okay, so now let me talk a little bit about what I think, what are the reasons why data scientists have a little confidence in the input and output of their analytics work by contrasting how traditional software development differs from data-centric software development process. This observation about how traditional software development and data and centric development is based on our studies of a professional data scientist. But what I also want to mention here is that some of these my findings and observations are actually supported by and aligned with other empirical studies on how AI and machine learning impact or big data impacts software development, which is some of these studies are done by other people at Microsoft and Google and also in academia as well. So I have some references here. Okay, so how is it traditional and big data analytics different? Let's consider the example of writing big data analytics applications using platforms like big data system platforms such as Spark or Apache Spark or Hadoop or Google's Dataflow. In traditional development, you write software, you run them, you test them and debug, and if there's a bug, fix it or repair, and you repeat this process. When you're writing this big data analytics application, you develop locally, but when you are developing locally, you may not have a full understanding of entire data, like a terabyte or petabyte scale data that's stored in, let's say, cloud or some remote data storage. So, as you develop the application, you also test locally, but often use very sample data, let's say like 100 megabytes of data downloaded from the entire data set. Then you execute this job or a software application on the cloud on the larger data set, hoping that it will work. Sometimes several hours later, maybe getting a coffee, you come back and you realize that job crashed. In this case, then you have a strong signal of a failure, such as exception and process died, right? Or sometimes you actually get something like a suspicious output. For example, predicting that median two-bedroom house in Kansas City is like $20 million, right? Which is sort of, very suspicious, right? Then people try to really debug this by trial and error, by fixing their, the code, and then repeat this process. Now, let me dig into kind of different aspects of this development to highlight some of these differences, why these differences appear. The first, the data is really large and remote, stored in a remote storage and also distributed. So it's never really local, right? Because these terabytes or petabytes of data doesn't fit into your machine, right? So, often this means that you develop with only subset of data or partial view of entire data, which is never known because also data is continuously evolving. And because you write software without seeing the entire outcome, entire input, it's actually very difficult to write expected output. Like this whole idea of writing a unit test where you give some input and know what is expected output, this kinds of a paradigm is very difficult to hold in this big data analytics development. More importantly, because you're writing these heuristic-based, often probabilistic, stochastic or predictive analytics application, it is inherently challenging to define what should be a correct behavior, right? Therefore, it's very difficult to define what is failures, or failures are hard to define. Like in the case of job crash, it's easy, but in the case of a suspicious output or anomaly data, it's even hard to define what incorrect software behavior means. Another challenge that's associated with that is that you don't really have a good visibility into the pipeline that data analytics application run. The underlying system stack is extremely complex. Why? Because to process these large, huge data in an efficient manner, these runtime systems and frameworks has a very complex scheduling mechanism, cluster management, data partitioning scheme, distributed and parallel job execution, fault tolerance, and straggler management. So these underlying systems is built with a kind of performance in concern, but not the debuggability and traceability in concern. So there's a less visibility into what's going on underneath. And also, there's a gap between physical and logical execution of analytics or applications you write. Why? Because these frameworks provide API, and these analytics queries that people write could be highly optimized and lazily executed. Because the user-defined code the application developer write is often interleaved with the execution of a framework code, right? So it's what the code you write is maybe different from how it's executed, right? So for example, if you just look at the execution log, like from, let's say, Apache Spark application, you can see like number of the worker node, job status in individual node, and overall progress to job rates, and like, how many workers are like being utilized and things like that. But you don't really get the logical view of execution, like, how which input generates which intermediate result and how that translates to the final outcome. And right now, if there is a failure, therefore, like you get an exception, like it's very hard to know which input contributed to which output. Because the data is in the distributed, these processing framework, and these frameworks provide almost no visibility or data provenance support. Okay, I'm going to stop here a little bit. I see some questions popped up in Q&A window. Let me read. It's a question from Aishan Rao. How do we plan for extracting relevant software artifacts such that we get relevant insight? Are there any common processes with regard to this? Or should we use existing API or individual script where we can modify what type of data we want? How is it going to affect the reproducibility of experiment from broader perspective? So this question is about like extracting like features from data to get relevant insight. So in our study of a professional data scientist, we actually saw a range of applications or different format of data being analyzed. Like for example, game data or speech data or like image data. So I think that the feature extraction really depends on the kind of domain that you work on, as well as the task that the data scientist is working on. If there is right now like the process or guidelines for data extraction for each of these domains, based on the study I have conducted, I do not think that they actually have it. Actually, one of the takeaway message from the study was like data scientists were echoing the needs for having these kind of guidelines and practices, best practices to share among the data scientists, because many of them seem to repeat some of these work, or like they wish they could share lessons learned themselves with other people. So short answer is like, I don't think there is a guideline yet. But I do think that with the rise of data science right now over the years, or even after my study, like it has been like, several years now from the beginning of the study, there's definitely need for and more interest in these data processing guidelines or feature extraction guidelines to increase reproducibility or traceability. All right. Okay, so let me now move on to the next question. Next part of my talk. So far we talked about how these data analytics fields are reshaping software development and some of these emerging role of a data scientist. Now I'm going to switch gears and talk about some examples of a research project that enhances or adapts software engineering, like the debugging and testing techniques for data analytics. In particular, for the past 5 years, my research group at UCLA focused on designing debugging and testing techniques for big data analytics application written in Apache Spark platform. This is a collaboration work with many students and postdocs at UCLA, and also collaborators in the area of like databases, big data system, and programming languages. I'm going to, before I talk about like individual project, let me first describe some of the insights or lessons that I have learned by trying to adapt these existing software engineering techniques for big data analytics domain. Adapting well-known ideas such as like interactive debugging or automated debugging in software engineering to this new domain of a big data actually was not straightforward. We learned that, you know, designing, for example, like interactive design debugging primitive to emulate like GDB or Eclipse or IntelliJ kind of debugging experience actually requires like strong internal systems knowledge or re-engineering these runtimes to by understanding the internal execution model like job scheduling and materialization scheme. And also, you know, this kind of providing debuggability or traceability require us to modify the runtime, right? The framework itself. But you know what was also really you know comforting for us or exciting for us is that you know abstraction, which is sort of recurring theme in our field of software engineering research, is actually extremely powerful force in simplifying you know applications that analyze machine learning and big data and AI, right? So there's some hope that you know some of the insights that we are familiar with from our own field is actually powerful force in you know improving developer productivity in these domains. So let's talk about, so we start from interactive debugging. So we had our tools such as like you know GDB or like interactive debugger for a long time, right? Why would it be hard to do that in the like let's say cloud or like big data system setting? Because we actually learned early on that you know naive implementation of these breakpoint debugging would not work in this big data setting, because pausing the entire computation on the cluster could really reduce the throughput, right? And also it's clearly infeasible for user to inspect billions of records flowing through a particular variable in Dataflow pipeline using kind of regular watch point. So this idea of a step debugging where you set a breakpoint and trying to read the value or program state actually has to be reinvented for this kind of a data pipeline or big data analytics setting. So in 2015 and 16, around that time, we started with a kind of this project, BigDebug, as a first project, where we tried to redesign debug primitive or provide interactive debug primitive for big data analytics domain. So, you know, without going into kind of details of this technique, what this does is that big data does not pause program execution on the cluster or parallel execution of this complex data analytics application. Rather, it simulates breakpoint debugging by really understanding internal execution model and scheduling mechanism, and regenerate like program state from on demand. So if a programmer like set a breakpoint, we call it as a simulate breakpoint because the program flow doesn't stop, but rather if people ask for values at that point, we will regenerate from the latest materialization point or with latest point where the naturally the big data systems such as Apache Spark stores intermediate result and regenerate these program values. And because of like billions of records cannot be shipped to a user, we, stream processing using guard or predicate that user provides to find the values that matches user criteria and then deliver that user to the user. We also allow like real-time code and data repair by re-engineering runtime so that we can actually dispatch inject the new data or recompile the modified code and redispatch it throughout the pipeline and across the different nodes, right? And we also to allow like, debuggability and traceability, given some suspicious data or intermediate result the user pick, we allow backward tracing by building this data provenance capability, which I'm going to describe next. So what is a data provenance? Data provenance is well-known, long-studied problem in database community. It means given an output of a query, such as SQL query, we want to identify which input rows or subset of input tables that contribute to that particular outcome in, query result, right? So if you have, let's say, some query result that's wrong or suspicious, trying to figure out which input on these like original data contribute to this. So for those of us, for some of us who are familiar with the dynamic tainting or taint propagation in software engineering may think, oh, this is a solved problem. We've been doing this for many years. What's really interesting challenge in this domain of big data analytics is that when you're dealing with 1 terabyte or terabyte scale data, scalability poses new challenges. So it's not as simple as just doing taint analysis in, program by following control and data flow. The problem really is a systems problem or scalability problem about how do we enable these tracing at an extremely large scale. So what we have done in this work that appeared in VLDB is that to provide this traceability and data provenance, we re-engineer the runtime so that we can store these intermediate result table or like intermediate result input and output mapping table, which database people call as a lineage table, by figuring out when is exactly the time to store this, like at the stage granularity. And then also we built distributed optimized join algorithm to allow efficient tracing. So as you trace back across these terabytes of data, we don't have to look up all the intermediate result, but we try to use some of these partitioning scheme or underlying way that the data is partitioned and distributed to only lift the data that require for backward tracing. Then, in the next phase, after we built this interactive debugging, we started actually trying to bring some of these ideas of automated debugging to this domain. So we worked on this topic of automated debugging. In other words, like given the application program, or if there's some predicate or test function that says which output is incorrect, we wanted to identify a subset of input record that leads to faulty result. So this is the kind of problem that many of us as a software engineer researchers are familiar with, because like about 20 years ago, like for example, Andrea Zeller's group worked on this delta debugging, which is sort of isolates a subset of input leading to wrong result in the output. And we started this by actually combining some of these two mature ideas from two separate communities, like the data provenance that we have built, as well as applying this idea of a delta debugging that I mentioned just earlier. Delta debugging, for those of you who may not be familiar with, it's a process of like dividing original input set into subset and rerunning the data to see whether the same symptom of a failure appears. So at a kind of high level, similar to binary search, but it's more optimized in the sense that you actually have a clever scheme of like dividing subset and then retrying which one to try. So this idea of combining data provenance and delta debugging was extremely effective. In fact, we were able to really find the needle in the haystack, meaning few input records that from out of like a terabytes of input data that leads to a faulty behavior. But we actually also realized that that's still not enough. To make it really effective and interactive and like responsive debugging experience, we had to build a lot of systems optimization technique at the underlying framework level, like like a test case predicate pushdown, or like a prioritizing which backward trace to look at first, and some of the systems optimization about how we like avoid the retrial of a certain input, right? Okay, so this might be also another kind of good point to take some questions and answer. I see one question. Before I talk about like, I'm sorry, let me actually talk a little bit about this. Like I want to actually summarize debugging and then answer question before moving to testing. So in our experience, like, we were able to provide this interactive debugging experience while retaining these scalar properties of a big data system. By building provenance and debuggability, we caused some overhead, like, total overhead about 35%. But we were able to provide this interactive debugging experience, which was not present for most developers because most people currently use only post-mortem analysis to do debugging. Also compared to like, some of the other techniques out there, by building these data provenance and storing like input-output mappings, like lineage tables using in-memory storage and doing distributed like optimized join, we were able to provide like data provenance or traceability functionality that's orders of a magnitude faster than some of the conventional techniques that may store input, output, mappings in some traditional like RDBMS type of system. Also, by combining these data provenance and delta debugging and building many systems optimization, we actually show that we can do this debugging like much faster than just a naive application of delta debugging. In fact, we were really surprised that, because big data processing takes a long time, when you build all these debugging primitive, we can actually debug much faster than even the original job run, because we could like really zero into re-execution of a small subset of data, therefore reducing the debugging time. All right, so let me come back and now try to answer some of the questions. Are there any questions?
And Miriam, if you don't mind, may I just read aloud for you?
Yeah, that would be good.
My job. Okay.
Yes.
So this question's from Fabio Calepato. In the beginning of your talk, when you said the software engineering practices need to be adapted for data analytics, what other practices other than testing and debugging do you think need to be adapted and why? And what changes would you recommend? Thank you.
Okay, so I think there are maybe two different like actors for needing to adapt. One is the developer who's actually writing applications. So in some sense, for them, like it's going to be about processes and guidelines. The other actor is researchers, us like software engineering researchers, who need to provide these supporting tools and techniques so that they can enhance the developer productivity in writing big data analytics. So my talk currently focuses a little bit more on the research audience side. Like, so I just share sort of my experience of redesigning, debugging, and testing for big data analytics. And later I'm going to talk about some open problems that we can work on. But for the developer side, like, what do I need to be productive as a data scientist? I think that's, the guidelines and best practices need to be shared. And there's also some emerging work that try to categorize these like kind of recurring processes or guidelines. So for example, like Amarshi Arrow's work that I just mentioned like about 10 minutes ago, which is like how AI impacts software engineering. They have a very nice actually process diagram about like kind of a divides like data scientists into multiple steps, and then like, you know, what kinds of processes they need to follow in individual step, right? So my answer is that yes, there's like two different audience. Right now I'm talking a little bit more on the research side, but there's also developer side or processes work that needs to be done. In terms of a research side, I'm also focusing a little bit more on testing and debugging and traceability, but I think there is like more work for us to work on. Like for example, like designing systems with, or architecting systems with this debuggability or productivity or traceability in mind, right? So I think like, you know, for example, like what is the good design patterns that we need to follow? Or what is a good like architecture styles we need for building these systems? That's a like great topic for us to really investigate.
Related to this one, I have one question. So maybe in software engineering process, we start from requirements, right? So is it the question is asking about what other part other than the debugging and testing? How about data quality? Can we think that data quality itself is a validation requirement in our traditional software engineering?
I'm sorry, Unji, like what is the data quality exactly what? Like
so checking the data quality, it's a responsibility of the software engineers or data scientists, or how the software engineering practice or software engineering technology can help to make sure the data quality is good enough.
Oh, okay. So let me try to actually dissect this question into a number of things, right? Like, so I'm probably less familiar with the research and requirements engineering, but definitely true that there's much more room for like reinventing sort of formalism or tools and techniques to even specify what should be the behavior or expected behavior for these predictive like AI ML based system, right? So I think there's a much more research to be done for like requirements engineering researchers to work on, right? Because specifying what is the correct behavior is challenging. The second thing that I want to mention is that this issue of data quality is not an issue for a single segment. In fact, when I did this interview study of individual data scientists, one of the kind of these tension that often came up is that data scientists thought that they got the data, right? The data wasn't clean, right? And, you know, but data is not the data they collected. So they think often like it should have come with some schema or description, but such things are never really present in practice. And also data scientists often complained about the fact that, you know, they had to fix the data before the analysis as if it is their job. And oftentimes they thought it should be like an instrumental engineer, like a data engineer who instrument the pipeline should have fixed it. So it is definitely true that data scientists, it's not like a single person's job. It's actually collaboration and interaction, and often there's a tension, right? Because, you know, this responsibility of a cleaning, analysis, and data collection is like continuously evolving, and people are trying to figure out, right? Like, so the second question, my answer is like, it's never really clear division. In fact, I think that makes this problem a little more challenging. Yeah, so. All right. So now I want to actually kind of talk a little bit about our work on like testing for big data analytics. So let's now look at like, you know, what people are doing to test these, you know, big data analytics application. The first option is actually sample the data and then it's usually done during the like kind of earlier local testing time. You know, they download the first 100 megabytes of data or first like a million rows of data from like terabytes, like data storage is sitting remotely, and then they run the application. The problem is that these application data that you downloaded may not exercise most of the application behavior, so you may have a low coverage. And if you repeat this process to increase it, you know, like data coverage, then you could like, you know, have a very long, like increase the local testing time. The other option is maybe use some traditional technique that we have, right? Like, is it applicable? So consider some of the well-known techniques, like such as a symbolic execution based or concurrent execution for like these analytics application. Are they applicable? Unfortunately, very difficult to apply as is. The reason why is that these systems, the framework code that I talked about as Apache Spark or Hadoop runtime, this is often a million lines of code, even though it has a very clean semantics. So if you apply, let's say Java Pathfinder or symbolic execution, without abstraction, you cannot handle this complexity of a code. Let me go a little bit deeper by giving an example of a big data analytics application. So for example, in the bottom, you see Apache Spark application that does some data processing written in Scala. And let me now talk about what is these big data analytics applications like. So first, they have these relational skeletons, such as a map or a filter or a group by or reduce by. These are like an API that's provided by, let's say, Apache Spark framework. Then what data scientists do is that they write their custom application logic in terms of user-defined application code, or what people call as a user-defined function. So this usually involves like processing the data or like parsing the data and computing some aggregate data. While you're doing it, these string operations are extremely common. And also, you know, because most of these analytics application compute the aggregate value, it's absolutely necessary to model collections or array. So what we have done in our work on big tests is to allow these white box testing of a big data analytics by sort of adapting symbolic execution-based technique to big data analytics domain. But as I said, this was not easy because the regular symbolic execution would not work due to the scale of the framework or runtime code. So what we have done is we abstracted this relation operators using first order logic. Then we actually did the user-defined function, the regular symbolic execution. Turns out that actually the framework code is very complex, so it's hard to do symbolically execute. But user-defined application code oftentimes is more manageable in the order of 100 or 500 lines of code. So it was actually possible to do symbolic execution, and we did some other extensions to make it more feasible, which I'm going to describe later in the slides. And then while we're doing it, we also handle things like array or string operations. And then we turn that into sort of a constraint and then use the theorem prover like a Z3 or like CVC4 to generate the concrete input data. Without going into really detail, let me briefly describe like how it works in 4 steps. So once we get the big data analytics application, we parse them and extract what people call as a like data DAG, like directed acyclic graph of these relational operator. Each operator has a user-defined function, but we first get to structure the data. And as I said, the API of a map and filter might be like very implementation of filter and map or join could be very complex because it's done distributed and parallel manner. But the semantics is actually very clean. So what we have done is we turn that into sort of logical specification. And while we're doing it, we are also handling like cases as, like thoroughly in terms of terminating cases or non-terminating cases, because data flow could stop as for certain operators. So for example, join, we're handling cases where, you know, 2 tables match with the same key, like inner join, so generates a data flow, but also like left table and right table doesn't, like has a key on one side, but not the other. So that it doesn't create the combined flow. So we are handling those kinds of things and writing them very cleanly using first order logic. Then when it comes to the code associated with these API call, like usually these are like application code that's passed as an argument to these higher order functions such as map and filter, we would symbolically execute them, right? And while we are doing it, we handle strings, collections, and tuples, because most of these data is stored as tuples, and then we need to actually also handle collections to compute the aggregate value. Then for individual, we combine this symbolic constraint we got from symbolic execution with the first order logic of a data flow operator, put them together. And then for individual path, which we call as joint data flow and UDF path, we will convert them into sort of a logical constraint, which has some integer constraint, Boolean constraint, and string constraint. And then we will solve these constraints individually using CVC4 or Z3 and generate concrete input data. So in other words, what we are doing is that given the big data analytics application that user or data scientists write, we comprehensively model individual program path. Then for each program path, we're trying to generate the input, like a synthetic input, the exercise path to help with the testing. So in our evaluation, we measure improvement in terms of coverage or fault detection capability and also test size or test reduction perspective compared to some of the existing techniques. What I want to mention is that while we're doing this study, unlike many C or Java code where we have many testing benchmark or bug benchmark, we didn't really have a bug benchmark for big data analytics application. So we also had to build some of these benchmark about what are the faulty data flow program errors, and then we injected them into some of the existing programs using some of these insights we found from empirical study of a Stack Overflow and generated our own benchmark. So in this work, we used some of 7 subject program application from earlier work, and all these applications were, has a complex aspects. It uses a diverse set of a data flow operator, string, arithmetic operation, and also deals with the tuples and arrays, right? While we're doing symbolic execution, we actually have a parameter that we need to set, which is kind of common in symbolic execution, which is how many times you will unroll the loop. So that takes a parameter which a K as an input, and then we'll unroll these program path and then find the concrete input for individual path. As I said, while we are doing this, we had to build faulty big data analytics application fault. In this case, we actually identified 7 different types of fault type based on our studies of Stack Overflow that uses Apache Spark, libraries, and application. We studied top 50 posts in depth and then taxonomized into 7 bug types. And so, for example, wrong join type is using wrong API of a join, right? Or key value swap is swapping key value pairs and then misinterpreting it. So we added these individual fault types injected into application to help with our evaluation. So yeah, this is an example where we injected fault type of incorrect column selection by actually reading a wrong column than the other one. Okay, so we were initially measuring some of the improvement in code coverage compared to some alternative technique. So in 2013, techniques such as Setch was targeting Apache big data analytics application written in Apache Pig, but it actually doesn't only model data flow operator, but looks at these application code that data scientists write as uninterpreted function, meaning black box. So because we do white box symbolic execution, we wanted to see how much code coverage that we actually improve. This is a chart to shows that, by doing this, our technique could improve this path coverage for about 80% compared to some of the existing technique. And the coverage is even bigger than the original entire data set. Why? Because, entire data set might be order of gigabytes or terabytes, but may not exercise every program path. But because we generate synthetic data for individual path, we can actually improve code coverage. Then we also looked at fault detection capability. For example, you know, how these techniques work, like a big test or such, work against finding these detective fault. And we find that these improvement code coverage actually directly translate to fault detection capability improvement, because we know more about like potential errors that could happen in application code, right? Because application code is kind of the complex part where you could do like parsing of data, like processing data, you know, like segmentation of data and things like that. This last slide on evaluation result is actually most exciting to me. What we showed is that by doing this synthetic data generation to test the big data analytics application, we can significantly reduce the data required to achieve high code coverage. So entire data could be in terms of order of, let's say like 10, like order of millions and 100 million. But by generating synthetic data, we found that we only need order of like 30 record to actually have a similar or even higher code coverage. This is really exciting to us because what people think is the big data analytics application hard to test because it requires large data. No, if you're very clever in understanding the application behavior and modeling it, you can actually reduce it. Maybe this could tell us that, you know, big data analytics application could, you know, because it's also written by developers, right? It's actually logic that people write, right? So if you find the right level of abstraction, we could really get a handle on this problem and simplify the data it requires for testing. This data reduction translates to almost like a 200 speed up in testing, even against the bigger data, right? Because we can now do local testing with this small data, and it's much faster than running these application on a cluster using lots of machines. All right, so before I talk about some of the open research directions, I want to stop here a little bit and maybe solicit some questions, if there's any.
I have one quick question. So you talked about how we measure other technologies. How about that? So is there any property we can formally verify for the big data analytics applications? Usually the correctness is difficult, but how about robustness? Can you talk about robustness? Is it possible to formally verify in this case?
I don't have an actually good answer for this question. You know, what I can say is that the correctness is a big concern, but not the only concern. You know, for example, like performance was a big concern, which I'm going to talk about now. You know, I didn't really hear robustness very much, but I could imagine robustness is also a good concern. How to specify robustness might be also a very challenging problem. But for now, like, you know, so Unji, I agree with you that this is an important topic. Do I have an answer or a concrete problem? Not yet.
I wondered because correctness is really challenging. We don't want to compromise, but that means we are going to leave some room for some incorrect input, right? That's why that's really the core of the robustness matters. So that was my concern. But still,
absolutely. I resonate with you, the need, right? So,
all right.
Okay, so now, you know, I share some examples of, you know, my own group's work on, like, you know, software engineering for data analytics. Now I want to talk about some, like, you know, open problems in this domain, which I hope that our community kind of work together. So when we look at our own community, software engineering, you know, here is a sort of roadmap that I see for accelerating data-centric development. For the past like almost 15, 20 years, there has been tremendous focus on applying data analytics to software engineering due to the availability of a larger repository data such as GitHub and Stack Overflow, and also rise of a research community such as the mining software repository. In the future, I hope to see our community in software engineering really collaborate deeply and with communities in big data systems, machine learning and databases and AI to really design tools to improve these developer productivity. And also, in my opinion, like, to provide the debuggability and testability as a first-class concern, we need to develop these software engineering tools, not as a hindsight after these frameworks are developed, but together develop it with the development of the runtimes and framework so that these debuggability and testability could be built into this framework as a primary concern. So now for in the next several slides, let me share some like insights and directions that which I hope that our community could go. The first problem that I see is that how to define correctness or even how to define bugs in this new domain of data analytics or AI and machine learning. My view is that this problem, it should be, the defining how to define bugs should be done both based on data and code. What you see on here, I draw this arrow where software engineering meets database. The reason why I drew this little diagram is to emphasize that I see interest from both the community, but to do really meaningful work, we need to really interact and work together. So when you look at database community, there has been a lot of work on data error diagnosis in database community by looking at characteristics such as data distribution, functional dependencies, schema mismatch, right? And our own software engineering community also have done much empirical work on identifying like kind of bug pattern, right? Like trying to understand from history of a code evolution to see which API usages lead to bug, right? And I think what we need is to combine these insights to define what data analytics debug mean. Same for the program repair. If you look at sort of the work coming from database community, there has been a lot of work on database cleaning, data repair, data wrangling. These are really well-studied topics in databases. But all of them just look at the data, but not the code. You know, it's very difficult to talk about how to repair this when the code and data needs to be repaired together or together with the, you know, sort of understanding. So our community also recently for the last like 10, 15 years focused on a lot of automated repair techniques, but mostly like, you know, injecting mutation and re-evaluating their code. And I see some tremendous opportunity where some of this work on data repair could be done together with the kind of code repair. The direction that I see, which kind of goes with maybe some of the questions that the Unji asked, is that, you know, we need to look at just beyond the correctness. So, for example, performance debugging might be a very important topic in this new domain. So one of my postdoc, Qian Zhang, actually did the manual inspection of a top 200 Spark-related posts. This pie chart shows the distribution. Actually, performance is like a biggest question category when it comes to big data analytics, which was surprising to me because I also did many like mining software repository research, especially with my recent PhD graduate, Titian Zhang. We looked at a lot of like API usage mining and error detection in Stack Overflow and GitHub. So we knew that for a lot of other desktop application, API usage is a big issue. But it's actually much small pie of the chart. when we look at this, the performance issues, these performance issues are actually very complex because usually the question is related to configuration, tuning, scaling, unbalanced tasks like I/O or memory related issue, right? So this is not just like correctness issue. This is also more like an environment configuration, system configuration issue. And in my opinion, in order to do, for example, performance debugging, it's really important to look at the vertical stack of how this AI, machine learning, big data analytics application runs on complex environment. So, for example, like there's some of the work coming from systems community that try to estimate performance based on data size. There has been some work coming from database community, try to optimize the correct performance based on cost model. There is also some of the work on like, computation and data skews. Actually, some of the work is done in my group, but looking at big data analytics, the computation and data skew issues. And there's also causal monitoring coming from systems community. But I also find that all this work is kind of looking at single aspects of this environment. And what we need is a really comprehensive view on these vertical stack to do some meaningful performance debugging. My last slide is that, when it comes to like, defining correctness, we also need to relax the kind of strict notion of what incorrect behavior means or what could be the potential root cause. So, we as a software engineering researcher often assume that there's unit test or, clean specification that says that this is incorrect behavior and there is a like oracle that exists. I think that for predictive, probabilistic, stochastic, like machine learning based software system, specifying what is the correct behavior is a really big challenge. So, there has been some work on, for example, metamorphic testing by trying to relate the changes in input to changes in output. Some of these ideas actually have been recently picked up by testing deep neural network, or self-driving vehicles, like deep test, and some of these references all use this idea of a metamorphic testing. But in my opinion, still metamorphic testing relationship used in these testing systems is very primitive. Means like if you perturb input in a certain way, you still expect the same classification result. And so how do we allow people to meaningfully define these metamorphic relationship or even discover them is a big challenge. Another thing that I want to mention is that, when it comes to root cause, there may not be a root cause or like the single biggest cause. This is again, when it comes to try to identify cause, it's actually attributing degree of importance on potential problems. And along this line, machine learning community has done a lot of work in training step debugging or influence function-based model debugging. And these are all trying to use some of the mathematics to attribute degree of importance on like which input leads to the outcome of a prediction. And I think we need to kind of work together with this kind of community so that we can quantify the importance when debugging like faulty inputs for big data analytics. So this is my last slide. In conclusion, we are at an inflection point, and somehow it's really interesting and exciting time for our community. But right now, when I look at the literature of where our colleagues and myself, everyone focusing on is that there's more emphasis on applying like these techniques from AI, machine learning, and applying to software engineering problems such as defect prediction or repair and code recommendation compared to enhancing techniques for these new type of AI ML-based system. And I think this is about time that we should really rethink our research community's contribution and how to redesign them for this new rising field of AI, machine learning, and big data. And I think there are many exciting directions that we should carve out and we could work together. With that, I want to end our talk that this is a really exciting time for software engineering for data analytics. And I think that these rise of a field need awesome software engineering tool, which we as a community could really contribute. I want to sort of acknowledge my collaborator, especially my recent PhD student who graduated, Mohamed Ali Gouza. He has been really the person who took this like work on big data debugging and big data testing. He's actually starting new position at Virginia Tech as a tenure track faculty member. And I want to also thank like my collaborator, all other collaborators who work on this studies of a data scientist at Microsoft Research, as well as the redesign of debugging and testing techniques at UCLA. I want to thank the sponsors, NSF, the ONR, Samsung, and Intel. And actually, many of these tools I mentioned today is all available online. You can find them linked from my website. And yeah, with that, I can take more questions.
Thank you, Mirang. So I have one question actually to revisit the correctness again. So correctness is with respect to the ACE specification we are checking against. ACE specification often available that is any simpler than the implementation for a data analytic program? If not, what are we talking about? Have implicit expectations or post-hoc judgments? What are they?
Okay, great question. So I think we actually had this debate. We recently had a software engineering for machine learning doc right before the pandemic actually spread in late February. And this was actually the kind of the hot debate point when we actually had our AI and software engineering researchers together. Many of the software engineering researchers in the room actually said, we need to talk about specification first. What is a specification? Because then we can define what is the correctness. And some of the industry people and also like machine learning, AI people, and some of the even software engineering people were saying like, yeah, the challenge is that we don't have it written, right? We have some higher level tasks that we want to do, like such as like identifying cat, right? But we don't really have a specification when cats are twisted and like cats in with the other animals, like, it's very hard, right? So, here's my personal take. This is not a science or research answer, but my personal take. I think one group of us, like camp, is going to have to, or will work on, like redesigning specification technique or redesigning tools to make it easier to write this specification, right? Like, so even though it could be incomplete partial specification, facilitate the process of writing, right? I think the other sort of a way that people do is that incorporate more user behavior when doing testing and debugging. So it's not that we start with some specification or some partial specification or lack of specification, but just to make it possible to incorporate user feedback kind of on the fly more easily, right? Like, so for example, if it is about detecting images, like if you detect it wrong, like you can easily see which one, you can easily expand to similar subset of data. So it could be more interactive technique, right? Like, so reading the question, yes, like sort of right now, the problem with defining what is a correct behavior is not a solved problem, right? And specification is absent in many of these data science work, right? It's often implicit, right? And other research communities also, work on this, like for example, anomaly detection, but even defining what anomaly is unsolved problem in my opinion, yeah.
All right, so we have two more questions. One question from Srida. What is your thought on the debugging deep learning frameworks?
Okay, so there has been some work on debugging deep framework. I sort of briefly mentioned it, but some of these work like LIME, influence function, training set debugging, they all target deep learning systems. These are some of the work done by machine learning community. I'm just mentioning some representative work, but for example, Xiangyu Zhang at Purdue University took some of these similar ideas and tried to identify like subset of training data set that leads to, you know, faulty behavior in DNN, you know, similar to kind of feature selection or similar to kind of regression testing. So I do think it is people in our community is now working on this topic, right? It's a very wordy topic, but it's also difficult topic, right? Because one, you know, defining, as I said, what is incorrect behavior requires some user input or some level of specification or half-written specification. The other one is the traceability itself, right? Like, so, you know, and it's not that like a single input leads to single output, right? There's no like mapping. Most of them are aggregated because these weights are learned, like weights of a neural network is learned from the training set, right? So that's why I think this is an important topic and we need to work together with our colleagues and, you know, statistics and machine learning so that we can kind of look at this issue of a model debugging comprehensively in the context of AI and ML-based system. Yeah. More questions? Yeah.
Yunji, I think you're mute.
Sorry, thanks. So questions from Ximin Wang. So great talk. From the perspective of DA and ML and DL for software engineering, automated test techniques are big trends, including testing and debugging activities. And SE for data analytics, can we anticipate that we are going to use more automated software engineering practices to be applied on machine learning and deep learning systems, or data-centric software, such as using machine learning deep learning to test the machine learning deep learning systems? In that case, how does human factor, non-automated, play in SE for data analytics? It's a great question.
So I think automated software engineering, like let's say debugging and testing has some like contribution was big component in improving productivity for big data analytics. But as you noted, I think that human factors are, or like good visualization, good human-centered, you know, interaction technique is going to play a very big role. Because, you know, oftentimes, like, you know, what I saw from data scientists that they have these like a chart or data and say, oh, this is anomaly, but where is this data this output came from, right? So in some sense, some of their existing questions rise from looking at this visualization, right? That's generated by data engineering pipeline. Right? So we need some automated technique, but I do think interactive, iterative, like techniques that could really incorporate the human investigation in an effective manner will play a really big role, right? Yeah, so I may have not mentioned the human-computer interaction aspects really strongly, but I do think really it's an exciting field. Yeah, in fact, like, you know, I'm actually have recently collaborated with some of the human interaction researchers in Berkeley and Harvard and built some of these visualization system for mining software repository work. And that has been a really wonderful experience and also sort of humbling experience for me, because I think we as a software engineering researcher or me, like, you know, we think like, oh, we did mine this pattern, we found something interesting and like, here's our data. But if you want to really put it into context of development, this visualization, navigation, interaction is an extremely important bit, right, to make it effective.
All right, any other further questions from audience or from Sam, our co-chair?
No questions on my end. Thank you very much, Marianne, for an exciting talk.
Thank you.
So it's right time. So, all right. So let me just appreciate our speaker, Marianne, again. So it was great insight. So it was very good time to review how those traditional software engineering techniques have been used for from our big data pioneer in our software engineering communities. I really appreciate. So, and also, it is very helpful from all the questions from our audience. We really appreciate for that one as well. All right, so thank you so much. Our talk or this session will be posted as a recording later. First will be posted in our cloud session and also be available for the YouTube as well. So, all right. So thank you.
Thank you, Unji. Thank you, Sam, for organizing this. And thank you, the audience, for great questions. I enjoyed this time. Yeah.
Thank you. Hopefully you'll find the more interesting talk from other program in this ICSE. Thank you.
Thank you.
Bye.
Bye.
Thank you so much again.
Thank you, Unji. I think by taking questions on the fly, I kind of spend more time in the talk, but I think that worked out really well.
That was helpful and efficient, but just wanted to have a more interactive kind of atmosphere with some
No, I felt that way.
Another person's voice. Thanks so much.
Yeah, bye.